Okay, in this problem we are applying a 600 Newton force to a crate, and this crate has the dimensions 1 meter by 1 meter by 1 meter, and the 600 Newton force is 0.8 meters off the ground. The center of mass of this crate is directly in the middle, and it's labeled point G. We're told that the crate weighs 50 kilograms, and the coefficient of static friction is 0.2. And we want to figure out what this acceleration of the center of mass is. So if we look at the free body diagram, we just need to identify all the forces that are acting on this crate. We know that we're going to have a weight that acts directly through the center of gravity. So this weight force is right here, and the weight is going to be equal to 50 times 9.81. We're going to have this 600 Newton force that's right here. We're going to have a frictional force, which is right over here. And the frictional force is pointing to the left because this 600 Newton force, which is pushing the box, is pushing the box towards the right, and frictional force opposes the motion. And then we're also going to have a normal force, and we're going to draw the normal force somewhere over here, and it is going to be a distance of x away from the center. And the reason that this normal force, let's call it NC, normal force of the crate, is not in the center is because this force P can either cause the crate to slide or tip. And we're going to assume that the crate slides. So this normal force is not directly in the center, but it has to balance out this 600 Newton force. So let's draw the kinematic diagram. And the kinematic diagram, we're going to have an acceleration towards the right, and this is going to be this 50 mass times the acceleration of the center of mass. Oops. 50 is our mass, so it's just 50 times the acceleration times the center of mass. Okay. Now, how do we go about figuring out the acceleration of the center of mass? Well, we have three equations. We have the sum of the forces in the x are equal to the mass times the acceleration of the center of gravity in the center of mass in the x direction. The sum of the forces in the y is equal to the mass times the acceleration of the center of mass in the y direction. And because this is just translating, we have the sum of the moments about point G is equal to 0 because there is no rotation. Now, this acceleration is only in the x direction, so this part of the equation right here, the sum of the forces in the y, it becomes equal to 0 because there is no acceleration in the y direction. And our forces, if we take positive to be up, we're going to have the normal force of C minus 50 times 9.81 is equal to 0. So this normal force of C is equal to 50 times 9.81, or 490 newtons. Okay, if we look at the sum of the forces in the x direction, we have, this is our positive direction, we're going to have 600 minus our frictional force, and our frictional force is going to be this mu k times nc. We know what this coefficient of friction is. It's 0.2. And we just figured out with the normal forces, it's 490. So this is going to be 0.2 times 490, and it's going to be equal to a mass which is 50 times the acceleration of g. And finally, we just have to deal with the sum of the moments equation. I'm going to just write it down here for more space. And if we take the sum of the moments about point G, we're going to have to deal with the 600 Newton force, this normal force, and this frictional force, because the weight is the only force that goes through the center of mass. And we're going to call this our positive rotation direction. When in doubt, I sort of go with the right hand rule. But if we look at what the sum of the moments is about this point, 600 is going to go tail first, so we're going to have minus 600 times this perpendicular distance. This perpendicular distance is going to be 0.3, right? Because it's 0.8 meters from the ground. We know the center of gravity is 0.5 meters away. It's right in the middle of this box. The box is 1 meter high, and what's left is 0.3 meters. So it's minus 600 times 0.3. This next force goes through the center of gravity, goes through the center of mass, so it has no moment. This normal force is going to be a positive nc times x. We don't know what this distance is, and we know what nc is. nc is 490. And this frictional force is going to go tail first, and it's going to be a minus 0.2 times 490 times 0.5. And this is equal to 0. So with this equation, we can solve for what x is, and we get x is equal to 0.467 meters. And this is good. This means that this box slides and it doesn't tip. If we had looked for x and x was greater than 0.5 meters, I get 0.5 because this is what we're calling our 0 right down the middle. And from here to here is going to be half of 1 meter, or 0.5 meters. So this is saying that our normal force is acting right here, which is 0.467 meters away. If our normal force was, say, acting at 0.6 meters away, well, it can't, because our box doesn't extend that far. So we'd have to rework the problem, and we'd have to use a normal force that is right at 0.5 meters, and we'd have to rework this problem. But we don't need to worry about that for this problem, because this x is less than this 0.5 meters, which means it occurs on the box, and that means that the box slides. Okay, so we can also solve right here. We can solve for our acceleration of g, acceleration of the center of mass, and we get the acceleration of our center of mass is equal to 10.04 meters per second squared. And it's positive, so it's going to the right.